Let's begin class. What we're going to do today is mainly a centripetal force experiment that we were just trying to get organized up here a little bit. We're going to do a little clicking first, and I'm going to show you a problem from an earlier midterm. Actually, there's a part of it from another semester. And then we'll do a little bit of discussion of Newton's laws. And we'll actually work on some problems instead of the concepts that we were going through last time. So there's the SARC schedule for today, this afternoon. We're going to do an alphanumeric question now. So turn on your clicker, hit the refresh key. And this one is by way of a survey, so it's basically a yes or no, and everybody's going to get a correct answer on this one. Okay. I have looked at my classwork grade since last night, yes or no. Just type in yes or no. Or type in A or B. And then hit the send key. When you get a check mark, can you guys do a count, please? If you typed in no, erase that and type in yes or type in B, please, instead of yes. No, do you still have a question? Oh, that was you. Okay, 5 seconds to vote. 5, 4, 3, 2, 1, 0. Isaac, you want to click in? Click a question. Do that real quick. Yeah, but it's a clicker question. Don't type in Y or yes, please. Type in A, if you please. Did you vote, Isaac? Okay. All right. Okay, students, it looks like most of you have looked at your classwork grade since last night, about 77% of you, so that's most of the class. And I just want to make known to you that what I updated last night was the clicking score. Okay, now there's only one figure for that, and that's the number of points you get. All right, now that's not the only part of your classwork grade, but it's a good part of it. Because we also have classwork, where we turn in lab data and stuff like that. And so the way that the classwork score goes is the following. For every question, you get 1 point for answering and another point if you get it correct. So you may have a score, and I can't remember how many is possible. I think it's maybe, is it 39? Does it say in the 36? Okay. So right now we've had certain, and this is the classwork grade since January 21st. That was our first official clicking session. Before that, your clicking and registration got you a bonus point, which are on the books. The other thing that I created for you is, actually, I think I'll go over this on the document cam. can you swap me over the document, Cam, please? Thank you. All right, I'll just use one of these pencils up here. All right, so there's some of our equipment for the centripetal force experiment. Let me clear this out of the way. Um, all right. Um, okay, attendance. I have two numbers for attendance. One is the number of days that you were present. Okay, so that's, I think it's a number between 0 and 7. And the other one is an attendance score. And that one is meant to encode the actual days that you were present. All right, now I wanted to make it a binary code, but unfortunately, the Canvas will not allow me to post a binary number. So for instance, if you have something like that looks like this, 1 0 0 1 1 1, that won't post in web courses. Let me put in one more 0 here. That won't, it'll drop this last 0 and it won't post this one either. All right. And so no, it'll keep this 0, but it'll drop this one. So it's not possible to give you a digital code, a binary code to symbolize which actual days you were here. Okay, now that's what I created it on my spreadsheet, but Canvas swallows all the zeros and stuff. It's a pain in the neck. Which days you were present. So, but I did give you a number. So here's the two things about it. Okay, the first one is the number of days that you were here. Now, if you have less than 7, it doesn't tell you which day. The second number, this score, does, but I couldn't put a digital version in there. So what I did was I typed in just a regular decimal number. And so what you have to do is convert the decimal number into a digital code. So for instance, 63 converts to binary. I don't know what it is. Let's see. Let's see, 1 3 7 15 31 63. So this means that you're so this means a 63 in binary is 0 1 1 1 1 1. I think. Let's check this out. Does anybody have a binary digital or decimal to binary conversion on their calculator? Computer science majors, do you have it? Is this correct for 63? One more? Yeah, so let's check it. Okay, this is 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 0. So 32 and 16 is 48, 56, 63. Okay, so what you guys have got is this. And unfortunately, I can create it on my spreadsheet as this, so I can see it. But because Canvas won't permit me to send it. It won't permit me to give it to you as a text entry. That would be fine. But you can't post any text into the web courses gradebook. It won't respect this 0 here. All right. And so, or any other zeros that are leading. So what this tells you is, so you're going to have to do this conversion yourself. Every spot. Here's the deal. 1, 2, 4, 8 powers of 2, and then turn it into. So take your decimal number, your decimal score, and convert it into binary. And it's a nice little exercise. Especially if you have, does anybody have a conversion mechanism on their calculator for binary to decimal and back? Nobody does? They don't make that on calculators? They all right, so you could probably do it on the internet too. There's probably a site for, decimal to binary. Anyway, so what this means is, okay, the first one is January 21st. January 21. And the last one is February 6th. Right? So when you figure out your binary code, this one would say, okay, I was here for January 21st, 23rd, blah, 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 on out to February 6th. So the last one, I think that's how many you got. Anyways, the last one is February 6th. So that allows you to check on your basically your attendance, and that's for any score. Okay, now if you didn't click anything on that day, then you have 0 for that. All right, so that's how that works. And I'm sorry I can't get you the decimal or the binary code for it, but it won't let me do it. Question?
Are those 7 days every day without class? Or are we at 7 days?
Yeah, it's attendance.
Okay.
So this tells you, the first number tells you how many days, but not which ones. This one, when you convert it to binary, will tell you which ones. Okay, so this one tells you how many, what? Go ahead.
I don't know. Sorry, the number was probably my head. I thought it was something else.
No, that's what it is. It's attendance. It's just a way to, because am I allowed to talk or what? All right. So this is for students that are concerned about their attendance and stuff. If you don't have like 7 up here, I think it is, max of 7, then you want to check which days you were absent. And this number will tell you which you were here and which you were absent. So, all right, so that's that. Can you switch me back to the laptop, please? Thank you. All right, now I want to continue with some stuff. By the way, this is a photograph of Newton's mathematical principles of natural philosophy, or as it's known by its Latin name, Principia, for principles. This is the first page, and it's pretty interesting to actually read it. He wrote it in Latin, so this is translated into English back in the 1800s. You can tell it's a really old page, but it's the earliest version in English that I could find. And somebody might have a more modern translation, but you would have to buy it. This one's open. This is an open resource. And you can see on this, he's got the concept of momentum on the first page. It's kind of interesting. He doesn't start anywhere like a normal physics class. So, this is what we really should be doing. Following this book, because he's the guy that invented all this. Let's go over this recent midterm problem. take a look at it anyways. So you can see it looks a lot like my normal homework problem. I try to use the same format in all problem-solving classes like this. So now this one is styled a little bit differently. It's got a diagram, Spider-Man and the George Washington Bridge, or Brooklyn. I guess that's the George Washington Bridge. Spider-Man's trap, 15 points. Peter Parker has Green Goblin webbed up from 2 directions, hanging from a horizontal stretch of the George Washington Bridge. Yeah, GWB. Big trouble for Gobby. One web number 1, tilts at an angle 33 degrees from vertical. And on the other side, the second web number 2, tilts at an angle of, what is that, 68? What is this? I can't read it. Is it 68? 68? Okay, from the vertical. In his chainmail suit, Gobby weighs 120 kilograms. Okay, so here 20 through 21 are the tasks. And this is because 3 of them are iClicker questions. But anyways, on this page, make a good sized free body diagram of Green Goblin, computing all forces and the force components. All right, label the diagram carefully and include strategic comments where you think it is good to do so. Do not write a novel, however. Show all your work. Now, that's kind of the stuff that we expect in this class, and that's how I wrote it in the semester, going by. So here's my diagram and stuff, and if you look at this, this is my solution that I posted way back then. You can see that we got triangles all over the place. All right. Hence, as I've said before, we're going to be doing right triangles till the cows come home. And this is an example of it. Now you can take a look at this. It'll be on YouTube, and you can jot down the specs. And I think we're going to do a version of this problem. We might even do this one a little bit later today. So that's kind of, and I'm giving you this so that this is from a midterm, just like we have a midterm coming up. All right. And so you might have probably would have a Spider-Man and Green Goblin, but you might have something else similar, with similar set of forces and so forth. So you can see that in this free body diagram right here, that's what this is called, which you could read about in chapter 5.7. You have 2 forces, the tension from web number 2 and the tension from web number 1, and then you have the downward weight force. All right, and you got to figure out, knowing the fact that Gobby is at rest right here, so there's the net force is 0. So these 3 vectors have to add up to zip zap. All right, and that's the key. It's dynamic equilibrium, and so the forces balance, and Gobby is he's trapped. So we might even do this one problem today in a few minutes. All right. Now, about Sir Isaac Newton's laws of motion. Here's the web address for this page in case you feel like looking at it. It says page number 78, and I guess 100878576 is the digital title for the Principia. Page number 78, I guess. And the reason it's it's the first page of his book, but it has like 77 pages of commentary and like a foreword, not by Newton, but by the translator and stuff like that. So you can jot this down now if you want. It's an enlightening to look at, because he's immediately going to attack centripetal force and gravitational force of the Earth around the moon. And you can see it in the first page where he's heading. So I highly recommend that you take a look at that. Now, I want to go to the document cam and let's do some more sketching here. All right, so that's my attendance stuff. Let's take a look at centripetal motion again. Okay, so this is page 2. And can you give me my pencil bag, pencil case there? Thank you. Let me get out a pen here. Now we're going to work out a problem or two here. First of all, we know that x of t for circular motion is equal to r times the cosine of omega t, and that y of t is equal to capital R, the radius of the circle, times the sine of omega t. And here's the geometric setup. I'll make the radius 3. Okay, so we have a maximum x, minimum x, maximum y up here. So this is the x-axis and this is the y-axis, and minimum y down here. And nice circle. Let's try not to make it look like too much like an egg. All right, and then so there's your circular path, and here's the generic location. So that's the vector r, little r boldface, and you could even write that r of t if you want. R standing for position, not radius. That's a customary notation for a vector of position, lowercase r. Sometimes you see other things, like sometimes people use a capital R in a vector form, but now this down here, this angle here is omega t. All right. So the angular frequency omega if it's just a circle is so, and the units of omega are hertz, which is also the same as seconds to the -1. All right. So the speed, let's see, omega times omega times the period, capital T, is equal to 2 pi. And so that means that omega is equal to 2 pi over capital T, the period. And that's the same as 2 pi times the frequency. Okay, times the linear frequency. All right. So omega is in seconds. Actually, you could write an omega in RPM, revolutions per minute. It would be in radians. So this is the giveaway that we're working in radians here. So let's figure this out now. Let's re-go through it or redo it. D by dt of x of t is equal to minus omega r sine of omega t. Okay, so that means that you've got a minus sign over here. So the x, this is Vx of t equals this stuff. So that's a sign that you've got a negative up here, wherever you are. It's got a negative component for Vx. Vy of t is equal to d by dt of y of t, first derivative, right? So y of t is r sine omega t. So this is, I'll put a plus sign. I usually don't, but just for clarity, positive omega r times cosine of omega t. All right, so that means that we've got some leftward Vx and we've got some upward Vy. All right, and they're proportional to this triangle here. So the R triangle would look like this, something like this. This is R of t, and here's omega t down here. All right, and so that being the case, the Vx, the velocity triangle will be proportional to this, but it'll be oriented differently. So let me write that up here in red. Okay, so your velocity triangle is going to be like this. So that's V of t in red. Okay. In other words, it's perpendicular to the position vector, and it's parallel or tangent to the path. And all velocity vectors are tangent to the path. Now, why are we doing this? Well, we're going to get some F equals ma out of this in just a second. Okay, let's do ax of t. Okay, so that's d squared by dt squared of x of t. Okay, so the second derivative with respect to time, or the first derivative of this one up here. So all that happens is minus omega squared r times, now we're back to cosine of omega t. All right, and similarly, ay of t is equal to second derivative with respect to time of y of t. And that's equal, now this one's a cos, so this is a first derivative of Vy of t. Right, so this is a cosine, so it brings out a minus sign and another factor of omega. So this is minus omega squared r times sine of omega t. All right, now this is important for us, right? Because you could write it this way. A of t, the vector, is equal to minus omega squared times r, the vector, as a function of time. All right, this is a vector statement that encodes in one statement these two up here. Okay, the minus omega squared. So what this means is if your r of t is up here in the first quadrant, which we kind of took as a generic thing, it means that your acceleration vector is the opposite direction. Omega squared, whatever it is, 52 RPM or 1000 RPM or anything like that, is squared is going to be positive, and the minus sign means the other direction. So this is going to be a different quantity, but it's going to be, the directionality is going to be opposite. So opposite direction to r of t. And it's got a different size. In fact, it's not a position, but direction-wise, it is opposite direction. And that is why acceleration vector is centripetal. Okay, so it's a centripetal. It's not centrifugal. It's toward the center. Now, you can have any other curved path, and you can, you could do it on parabola actually. There's a centripetal acceleration on a parabola as well as a tangential acceleration. So for instance, let me draw a small parabola here. I'll do a 45-degree launch using the 4 rectangles method. 3 blocks per side, 4 of them. Okay, so here's your launch point, here's your landing point, here's your apogee, and your parabola is like this. Now we know that the acceleration is downward. G is downward. So what that means is, though, that for instance, if you're right here and you have a velocity vector like this, so here's your velocity vector at that point. All right. Now, perpendicular to that is the centripetal acceleration. All right, so you got some centripetal acceleration changing the direction in this manner, perpendicular to the velocity. So that's A subscript C, right? But you also have some velocity parallel to the direction, or some acceleration parallel to the direction. Actually, it'd be anti-parallel. Okay, so you'd have some acceleration this way, so that would be A subscript tangential. Okay, so A subscript T. So, G is downward, all right? And what you've got is basically something like this. So here's G, here's A centripetal, here's A tangential. So in order to figure out this angle here, theta, you'd have to know exactly where on the parabola you are. And you figure out the angle basically by figuring out the angle of V and then going perpendicular to that, stuff like that. All right. So in other words, this would be the direction of V. That looks pretty good at that time. So the basic idea here is that anytime you have a curved path, you can get a tangential and a centripetal component of the motion. And the centripetal component of the motion is the important one for us, because that's the only acceleration you get if you're on a uniform circular motion. Now, if you're something like a parallel, you get a mixture. You get a little bit of each, and it's not as nice and uniform. It's more complicated to figure this out. That'd be a nice study problem. Figure out the equation of, for instance, A of C, a vector A of C as a function of time on a parabola. That inspires me to work this one out. I've never done that before. But, and the problem is that this one, the centripetal acceleration is a function of time, but it's not this nice. It's not as nice as this. This is circular motion here, uniform circular motion. And but this one you could do if you wanted to. It's be a trig nightmare. It's probably best to parameterize it by time. But now, let's go to the next page. We're going to do some centripetal motion stuff now. All right. Now, I want you to look up here. I've got a jury-rigged deal here that is pretty discombobulated, but all right, now look it up here. Everybody look. All right, so what I've got, let me stand up. You guys better clear out. I don't want to shoot somebody's eye out. Okay, now what you guys are going to be doing is you're going to have a clear plastic tube like this. There's going to be a weight at the end. Okay, now that's mg. It's a little bit of W equals mg. And then over here is a mass. Now we just use something out of the closet, but you can use like some sunglasses, or even a calculator. Calculator would probably be hard to tie up though. But anything that you can tie, like if you have what I was thinking is a model car. If you have a little model car or something like that, you could use it. If you have anything like that, hopefully something that's soft or not, totally going to poke somebody's eye out. So what you're going to do, this is going to be your orbiting object, okay? All right, and if you orbit it at just the right speed, you have a circular, this will be like your radius right here, okay? And the centripetal force will be provided by this thing down here, okay? And so you're going to want to measure the radius of the circle and figure out how many newtons of force you got down here in this weight. And and then you're going to time it so that you get a certain amount of revolutions. Count like 10 revolutions, then figure out your frequency and stuff. Right? So it goes like this. Okay. Now, so you want to do it without bonking yourself on the head. So, all right. Now notice I'm holding it down. Let me get it faster. Okay, slow it down. Okay. Now you want to experiment because obviously if you do that, 3 teams at each table, you're going to bonk somebody's eyes out. So you want to try to get it up here, and so this one, anyways, you're going to be doing this experiment, and it's going to take some time to get the hang of it. As you can see, it's a little tricky. So who's got something that, it would work if you have a pencil case. This will definitely not poke anybody's eyes out. But anything like that. Water bottle, water, it has to be lighter. It has to be lighter than this, the weight, and everybody's going to get a different weight. Question.
I was just gonna say, so the weight, everyone's spinning, you want to be about the same weight or less than you're gonna get.
Yeah. I didn't dismiss anybody. What? Are you going to the bathroom too?
No, I was waiting. I don't. Sorry.
Okay, so let's take a look. Let's make a sketch of the centripetal. The centripetal force experiment. Hopefully it's not an experiment of doom. But let's draw a picture. Let me do it in ink. Okay, so here's your tube, right? Okay, and I'm drawing it in perspective. And here's a circular path, some generic distance. And here's your string. Okay, and out here, I'll put a dot for the mass. Okay, and then the string, let me do the string in red. That'll help. Okay, so there's the string, and it goes down through the tube at the bottom, and then down here. So this is kind of a generic version, is the weight. And so the weight force is equal to mg. Now we're going to need some scales too. Do you know where? All right, I'm going to give you the key. So you're going to have to measure your weight at the scales. Just put a couple, 3 of them back there. All right. And so let's just label this. This is R. And you don't really need to know this, but you can mark your. We've also got some masking tape, so you can put a piece of masking tape on your string like right down here, so you can know that you're keeping that'll keep this radius constant. So if you can keep this little piece of masking tape down here at a constant height, that'll mean this is a constant radius here, and then you'll be able to make your measurements. All right. Now here's the free body diagram. So what we're thinking about is the mass m and the centripetal force on it, F subscript C, is equal to the weight force times minus r hat. Now, minus r hat is the radial unit vector. And it's equal to, if this is the y-axis down here, and this is the x-axis out this way, then the radial unit vector would be cosine omega t, comma sine omega t. In other words, it doesn't have any dimensions, but its length is equal to 1. So you don't really have to worry about it except to know that we're using it to change the direction, because down here on this weight, the free body diagram is downward like this. So this is mg, and it's getting some pull force upwards from the spinning. And so that means that over here, the centripetal acceleration is equal to the pull force, but in the opposite direction. So this is kind of like right here. This is like a pulley. It's like a pulley up there. In other words, it changes the direction from a downward weight force here to a centripetal force in a horizontal plane. So this is in the horizontal plane, or as close as you can get. And so so what you're going to be doing here is you're going to be measuring R and omega, all right? And you're going to compare that against mg. So calculate mg, measure or set the radius R, and in other words, like by using the masking tape, and try to keep the circle, and then measure the period t. Okay, and then calculate omega from that, and then correlate. Oh, you're going to need the mass of this object up here. So this, what should we call this? This is your planetary object. So this is the orbiting object. So this is like the moon, and the pull force is like the gravitational force of Earth on the moon. So measure that, get omega squared R. Okay, and hopefully, check this, is omega squared R equal to mg. So this is the weight force over here. Okay, you'll be able to calculate that in step 1. And this omega squared R you'll get from step 3 and step 2, all right? So here's our objective to see if this holds. Now, as you saw, it's going to be difficult to get it. Okay, so it's going to be tricky. But I want you to be patient. Try again, and I want you to measure. Do this. Oh, sorry. Move it up, you mean? So what I want you to, so let me go over that again. So you want to see if omega squared r is equal to mg, all right? So omega squared r you get from measurements 2 and 3. Mg you just get from the first calculation and measurement over at the scales. So measure these two masses, measure this mass, and then measure this one down here. You don't have to worry about mg of this one. Now you're going to get this question over there. Okay, thanks. Did you get some? Okay. We don't have any digital scales? Are you sure about that? Yeah, take a few minutes to look. Can you guys help him find digital scales? All right. So now I want you to do this times 4. So 4 times, so 4 different radii. All right. Now the thing about it is, if you change the radius, you're going to have to change omega squared. Okay, so it's going to be a different speed. So 4 speed radius sets. All right, and we want to check all 4 of them and then answer this question down here. You know, so your radius number 1 might be right on it, and radius 2 you might not. It might have a little slop in it, so they might be a little bit off. All right, so do that for 4. Let's see how close you can get. All right. Now, did you find anything? There's got to be some digital. Question? You're what?
Ready.
All right. Well, we're not quite ready yet. Does anyone have a question? Does anyone have a question? All right. Now what we're going to do is we're going to hand out some string up here and tubes, huh? Yeah, sure. Nothing? All right. So figure out your, let's get all the gear up in the front. Tyler will give you out a weight, and then you can use one of the, here's the thing, Tyler, hold up one of those tape spools of, okay, this, if you want, you can use one of these. If you have something else you want to use for your orbiting mass, go ahead. But if you don't, just use one of these spools. All right. Take this up to the front. And so come on up, get your weights, get your string, get a spool, get a tube. Can you help with the tubes, please, Quinn? I want you. Hold on. I want you to get the string cut for everybody. Take a tube and Kendra will cut the string for you. Matter of fact, I'll help with that. Kendra, here, I'll hold this for you. Next, this is forehand job. Next, you're gonna do this 33 times. You're probably gonna need. No, that's probably okay. Watch out for my finger. Gosh.
Are we assuming it's 90 degrees?
Yeah. It's not gonna be perfectly 90, but if you get it at just the right speed, it will be pretty good.
Yeah. And then, I mean, we're not accounting for any of the friction as like it's going over the tube.
Just keep your hands off the string. You could start with your hand controlling the string, but once you get the right frequency, you could take your hand off the string.
You don't use it, like you could use that instead.
Yeah, I understand. Yeah, we're gonna assume that that's smooth enough. String, anybody?
Don't grab it.
Next. String, wonderful string. String, wonderful string. La 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 la. Did you hear that at the Billy Joel concert? You did. No, you kidding me? Billy Joel's string. He did. That's one of his most famous. Give me some songs. I'm the piano man. So what? Give me some string. I'm the piano. String, string. Anybody want some string? String, glorious string. La la. That's from the musical Oliver Twist. You know, he has the famous line, "Sir, please, sir, may I have some more?" And then they have all these kind of songs and, little beggars in London and crooks singing and dancing and stuff like that. It's pretty hokey. String, wonderful string. And it's going to be a little tricky, so get your clicker out. It's going to be alphanumeric, and it's not going to be on the screen. Okay. So what we're going to do is go over to the document cam, and we'll work off the document cam. Okay. Come on, document cam. Come on, baby. Document cam. There we go. Okay. So what I want you to do is to hit the refresh key on your calculator, and you're going to type in some numbers. Now, don't type anything yet. I want you to know exactly what I want. And I want you to do the same number for each group. Okay? Now, you've all got a lot of different string lengths and stuff. Some of them will look really good. Okay? Some are a little shaky, but that's allowable in a lab experiment. You let the numbers do the talking, even if they look a little shaky. So what I want you to do, we're going to get 3 numbers in on one question. We're going to get your hanging weight, that's capital MG, and I saw a lot of you with using 100 grams, so that's 0.98, like this one here, okay? And then m omega squared r, that's the centripetal force on whatever the object is that you were using, like a key ring or whatever. And that's going to be in newtons. So and this is from somebody's paper, and I don't think it's the best one on their paper, but they had a weight force 0.98 newtons. Don't type them in yet. Cancel everything you just sent. You got to listen, because this is a tricky set of numbers to type in. All right. Now the last thing that I want is your radius, and all of this for your best trial. All right, so for this guy, it might be 0.475 meters. Okay, and those are his numbers. Now, here's why I just yelled at you about don't type it in the numbers yet. I don't want the symbols N or M, and I want 2 significant figures over here. So 0 and type in a 0 if you have a 0. You can't put a decimal point first. It has to be 0 point something. Comma. Right? You got to separate it with a comma. Then put in your a centripetal. So instead of 1.04 newtons, type in 1.04. And then comma. And then instead of 0.475 meters, just type in 0.475. And then hit the send key. All right, now you can do it. No spaces! You'll run out of space. There's got to be a comma. Are you sure? That can't be right. Okay. Instead of a comma, no, I don't want dashes. Instead of a comma, Put a slash. You have a division bar, right?
Yeah.
It should, now I know you're not. Has anybody seen the slash? It's in there.
There's a Z.
Let me see your clicker.
No, you're saying
I can't believe it. It used to have this. All right. Hold on. Let me see what to use. Okay. Here's what I want you to do. I'm going to go back here. Okay. So below. Okay. There's the decimal point. Okay. Below the decimal point is an up arrow key. And below that is an underscore. See it? Use the underscore. Okay, I just put an underscore for you. Okay, so do two more numbers with an underscore between them. Okay, I want three numbers, so I can only see one person with two underscores. Okay, there's somebody that ends with an underscore. And I see one person with a 0 and another with a 0.49. So everybody at the same team use the same numbers. I just want to see that. I can't believe it. You used to be able to write equations and stuff. Used to be, with this thing, you used to be able to write equations. Like
I know what you meant. You thought it was the division bar, but you just
I got caught napping in front of you. I got caught napping. Oh man, I'm in trouble for today. Because usually it's me catching you napping. Angel, did you get yours in yet? Since when is she your secretary? What a slacker.
a little slow until noon.
See, that's what happens. There's one over here too. I can't believe it. Whoop! It just went out of your hand. All right, hurry up. Yeah, this is looking good. Yeah. There's somebody that sent in 0.49, and that's it. That's one person. All right, you just redeemed yourself. It looks there's a lot of 0.49s. Some of these are pretty good. Nope, 0.99. You can't do that. You have to put a 0.99, not 0.99. So whoever did 0.99 and 0.22, you got to do it over. That's not three numbers, and you have to put zeros in front. Better do it again. You could type it in again if you want. It can handle, multiple. It can handle little bloops like that. I can't believe it. That shows you never used two at the same time. Spectacular flailing is more like it. Or no, an epic fail. Well, Well, the Invincible 2, usually you don't see a spectacular. Any fail is a spectacular fail, epic fail, because mere mortals would not be able to attain to the level of the Invincible 3 or the Invincible 2 under most conditions. So anytime you do see them mess up, it means an ordinary human being would not even be able to get close to it. So bad that, yeah, very high level. When klutziness comes in, it comes in at a high level. Okay, you got it? All right, who's still typing in their number? Your three numbers, I should say. I'm getting ticked off. All right, 10 seconds to finish. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Isaac, you got yours in? Good. All right. All right, let's take a look at some of this data. Oh, can you switch me over to the laptop? All right, let's take a look at some of this data. All right, let me make it bigger here. Okay, this will show up good. All right, so the first two numbers should be fairly close. These two are pretty good. Whoa, right on the money. These are pretty good. And then the reference is the third number. That'll allow us, what that'll do is I'll be able to process everybody's data and give a scatter chart and maybe find the pattern. Okay. So, and there's going to be some slop in here, like 0.49 and 0.54 here. That's not too bad. Here's one a little bit more slop, but a different mass. That should be encoded only in the middle number, because that's little m omega squared r. But this number over here is only the hanging mass. It's big M times G, right? So it shouldn't, none of this, what you're worried about is the fact that it uses a different mass, but everybody was using different masses, for the orbiting object. You had a cool one, but it was still a mass. And it'll show up only in the middle number, and then the first number is the hanging mass. So what I'll do is I'll probably calculate the ratio of hanging mass and m omega squared r, and then see, and then that would be, and that'll that'll give us a goodness of correlation between the two numbers, right? So you typed in your best one though, right? Yeah, okay. Yeah, no, these are looking good. Ooh, here's one a little bit up there. I remember looking at that paper. That's all right. The thing about it is, and everybody's going to get points on this. I'm not going to try to grade it right now, but I see a ton of 0.98. The 10 or the 100 gram weight. See, look at that, 0.978. That is pretty good. See, now look at this. Look at this. Look at these top two. Look at this. All right, so here's your hanging weight, 0.98 for both of those. Okay, good. The 100 gram weights. Now, 0.975, that's pretty good in this first line. The next one, 0.978, that's also pretty good. But notice the difference in the R's. 0.160 for the top one, 0.565 for the other one. So those are two, that's something about like this, and it's something about like this, all right? So two definitely different orbits, but definitely pretty nut. Whoa, look at this one, 0.98, 0.99, and a different R. So we're getting a good spread of good values at different R values. And that's how I'll plot the data. I'll get all this analyzed and stuff, and hopefully Thursday we'll be able to go through this data and stuff. All right. So that's good. That's good. Now we're gonna we're a little bit early. Uh, I think we can do another 5 problems. So I just saw it. Oh, these guys over here. Okay, let's go. Especially the guys over here by the back door, 1 foot out, the getaway table. Hold, no, we're not done yet. Hold on, I want to talk about homework. Let me just get this stuff out of the way. Now, here's your homework assignment. I want you to start working out the highlighted and annotated. There's a few annotated problems in chapter 5, all the way up to 5.7. All right, make that your study assignment between now and Thursday. All right. So, so I've highlighted several problems that I think are good, and I've annotated a few that I think are good. So go ahead from the beginning of chapter 5 all the way up to 5.7. All right. Question?
Oh, I was just saying where we start at, chapter 5.
I think 5.1. Yeah. All right, now you're dismissed. I'll see you next time.